You clicked on this video because you saw headlines claiming GPT 5.5 has finally cracked the code on complex software engineering tasks, and you need to know if that means your team can finally stop writing code. The reality is far more nuanced and critical for your business than a simple benchmark score suggests. We are about to dissect the dangerous gap between a model solving a theoretical problem and that same model actually shipping a reliable product to your customers. The latest evaluations on Program Bench show a startling trend. When top-tier models like GPT 5.5 High are tasked with rebuilding programs from scratch, they often produce code that works in isolation but fails the moment it touches a real, messy codebase. The data indicates that while GPT-5 achieved a 23.3% pass rate on complex enterprise problems, this number tells a misleading story. It captures the moment of initial success but ignores the chaotic reality of long-horizon development. Consider the difference between solving a puzzle and running a factory. Solving a puzzle is a deterministic event. You have a clear goal, a set of rules, and a single correct answer. If you get it wrong, you try again until the pieces fit. That is what benchmarks measure. They test a model's ability to find that single correct path through a static problem. But shipping software is not a puzzle. It is a continuous, non-deterministic process where the ground moves beneath your feet. Every time you change one line of code, you risk breaking something 3 layers deep in the dependency chain. The research reveals that current models struggle immensely with this non-deterministic state. They can often generate the initial logic flaw fix, but they lack the grounded reasoning required to maintain context across multiple files and external dependencies. When GPT-5.2 performs extensive refactoring overnight, it frequently produces monolithic, non-human-like code. This code might pass the initial test suite, but it does not adhere to the architectural standards that human engineers have built over years. The model does not understand the cost of the decision it just made. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is the thing that separates a benchmark victory from a production reality. The gap is defined by the cost of iteration. In a benchmark, if a model makes a mistake, the evaluator can simply reset the environment and try again. The model learns from the immediate feedback loop. In a live business workflow, every iteration carries a cost. If the AI diverges from human architectural standards, the human engineer must spend hours untangling the mess, often undoing the work the AI just did. This is why practitioners note that while the model can perform the heavy lifting, it still requires significant human intervention for decision-making. Earlier models were often described as lazy and indecisive. They would stall at the first sign of ambiguity. The newer iterations like GPT 5.5 High are faster at resolving the initial logic flaw. They push through the first hurdle with impressive speed, but speed does not equal reliability. The real failure mode in production is not syntax errors. It is the inability to recover autonomously from downstream integration failures. When the AI modifies a database schema, it often fails to account for how that change ripples through legacy systems that were never designed for its specific output format. This creates a paradox where high benchmark scores do not correlate with the ability to handle the long-horizon dependency chains required to ship a product. The evidence suggests that while GPT 5.5 High significantly outperforms Opus 4.7 on synthetic benchmarks, this superiority masks a critical divergence in real-world performance. The models are better at the initial guess, but they are not yet better at the long game of maintenance and integration. The perceived superiority of these models on isolated tasks suggests a future where full automation is imminent. But the data points to a different conclusion. Specialized agents or human-in-the-loop workflows are still required to validate the AI's solutions against architectural constraints. The immediate business value lies in augmentation rather than full automation. We are seeing a shift where the AI acts as a powerful junior developer who is incredibly fast but lacks the institutional memory of the codebase. This distinction is vital for anyone considering AI adoption in production. If you are betting on these models to replace your senior engineering team, you are betting on a capability that does not exist yet. The models can handle the repetitive, well-defined tasks. They can refactor legacy code faster than any human. But they cannot yet make the high-level architectural decisions that determine whether a system will scale, remain secure, or be maintainable 5 years from now. The absence of verified data on hypothetical variance highlights a knowledge gap regarding whether incremental model updates actually bridge the gap between theoretical task completion and reliable, maintainable business workflows. We must stop treating benchmark scores as a proxy for production readiness. The 23.3% pass rate is not a promise of autonomy. It is a measurement of how often a model can find a solution in a vacuum. The real metric we need to track is the time it takes a human to review, fix, and integrate the AI's output. Until that time drops to near zero, the model remains a tool, not a replacement. The future of software engineering is not about handing the keys to the AI and walking away. It is about building workflows where the AI handles the execution and the human handles the judgment. The shift from solving to shipping requires a fundamental change in how we view these tools. We need to design systems that assume the AI will make mistakes that are not syntax errors but architectural missteps. We need to build guardrails that catch these divergences before they reach production. This means prioritizing human-in-the-loop oversight over the illusion of full autonomy suggested by isolated benchmark victories. The technology is advancing rapidly, but the gap between what the model can do and what it can safely ship is still wide. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.